Alright, in this video we're going to talk about symmetry and even and odd functions. And so first of all, let's look at this graph here. You can see that we have some symmetry with respect to the x-axis. So for example, if you have a point here, we'll call this x, y. Then across the x-axis, the same distance away, you'll have a point down here. Notice the x value is going to be the same, but instead of being up this distance or down this distance, this would be minus y. And so here we have symmetry with respect to the x-axis. And in fact, this equation for this one here, this graph, is x equals the absolute value of y. Now, there's an algebra test, if we're just given the equation, that'll help us to determine if we have symmetry with respect to the x-axis. We basically substitute minus y for y, and we see if the equation is unaltered or unchanged. So prove that x equals the absolute value of y has symmetry with respect to the x-axis. And again, we're using this algebra test. Actually, it looks like I need a different pen. So let's start with x equals absolute value of y. We're going to replace y with minus y. Well, the thing about it, if you think about it, absolute value of 3 is 3, absolute value of negative 3 is 3. We're always going to get a positive value here. So absolute value of y and absolute value of minus y are going to end up giving you the same value. And so we could say that x equals the absolute value of y here. These are equal in value. And so when we replaced y with minus y, it turns out that this is equal to the original equation. It's unchanged. And so this, using this algebra test, we've shown that we have symmetry with respect to the x-axis. Notice basically what that's saying is whether we have y or minus y in here, x will be the same. Alright, let's move on to the next one here. So here we have symmetry with respect to the y-axis. You can see if I drew a line right here, if I have some point over here across the y-axis the same distance, I'll have a point on the other side. If this is xy, then over here, notice instead of going positive x, we're going the same distance, but it's going to be minus or negative. The y value is the same, because we're at the same height here. So again, we've got a test down here that talks about it. First of all, this is the graph of y equals x squared. And the algebra test for y-axis symmetry is here. So basically, notice what it says. To determine if the graph of an equation is symmetric with respect to the y-axis, substitute minus x for x and see if the equation is unaltered. And so this time, we'll start with y equals x squared. We're going to replace x with minus x. Whoops. And if you multiply a minus x times a minus x, you're going to get a positive x squared. And so notice the equation is unchanged or unaltered. And so, again, what we just did here, we had to prove that y equals x squared has symmetry with respect to the y-axis. So I want to point out something here. Certainly you can see from the graph that it has that symmetry, but you can't say that that's a proof. Just look at the graph. This is a way that we can algebraically prove that we have that kind of symmetry. All right, let's move on to the last one. So here we have some kind of symmetry going on. Maybe it's not as obvious as the others. So if I take some point up here, this would be xy. Notice on the other side, we could actually draw a line here. So we have a distance from the origin to here, and if you go to the opposite side, the same distance, you find a point as well. Notice in this case, the x value, instead of being this distance here, it'll be minus that amount, so minus x. And instead of being this distance y, we're down that distance, so this will be minus y. And so for any point I choose over here, if I draw a line through the origin here, on the opposite side I'll find another point. This is what we call symmetry with respect to the origin. And just as before, we have an algebra test that we can use to prove that we have symmetry with respect to the origin. Now you may recall this is the graph of y equals x cubed. I call it the John Travolta. And so if we take y equals x cubed, and again we want to prove that y equals x cubed has, and I'm just going to say origin symmetry. Also we would, or we could say symmetry with respect to the origin. Okay, so we would notice what it says here. We're going to replace x with minus x and y with minus y. Let's do that. Notice we're cubing a minus x. So here we have minus y is equal to, if you multiply 3 minus x's, you're going to get x cubed, and your sign's going to be negative. So it's minus x cubed. Now if I multiply both sides by -1, won't I get y equals x cubed? And so again, when we replace x and y with their opposites, we end up with the same equation, or it's unaltered. And so in this case, yes, we have shown that this has origin symmetry. So this is how we would do that algebraically. All right, so I just want to point something out to kind of summarize here. To prove that we have x-axis symmetry, we replaced y with minus y. So that's for x-axis symmetry. So we basically replaced the opposite variable. Same thing here, to prove that we have y-axis symmetry, we replaced x with minus x. And finally, for origin symmetry, we replaced both. All right, let's go ahead and move on to do some more examples. So it says, determine whether the graph of each relation is symmetric with respect to the x-axis, y-axis, and the origin. All right, so to see if we have x-axis symmetry, we're going to replace y with minus y. And so that's going to be y squared. And so notice we're unaltered when we replace y with minus y. So yes, we do have x-axis symmetry. What about y-axis symmetry? Well, if we replace x with minus x, again, if we're looking at y-axis symmetry, we're replacing the opposite variable. So that would be x with minus x. Now notice if I multiplied both sides by -1 so that I could get the x, I would end up having opposite signs over here. And so this one is, the answer is no, because our equation is not unchanged. It's definitely changed. Finally, do we have origin symmetry? Well, replace x with minus x and replace y with minus y. So we have minus x equals y squared plus 2. Now again, I need an x on the left, so I'll multiply everything by -1. I get x equals minus y squared minus 2. And notice that is not the same as the original, and so no, we don't have y-axis symmetry. I'm sorry, origin symmetry. In fact, the only thing we had was x-axis symmetry. Alright, so we'll do the same thing here. We'll check for x-axis symmetry, y-axis symmetry, and origin. So with x-axis symmetry, to test for that, we replace x with minus x. Notice this minus x squared becomes x squared. And so here we can say yes, we have x-axis symmetry when we replace, oops, I messed that up. I just did the test for y-axis symmetry. I should have replaced y with minus y. So I'm going to switch these here. So here I'm going to replace y with a minus y. So you can see it's quite similar here. Because if you take anything to an even power, even if it's negative, you're going to end up with a positive value there. Minus y times minus y is y squared, times another minus y times another y, minus y. You're going to end up with y to the 4th. You're going to get a positive answer for any even power. So we do have x-axis symmetry. So basically, these proofs are switched. Remember, to check for x-axis symmetry, you replace y, so that's what I did here. For y-axis symmetry, you replace x. So origin symmetry, we replace both. And you can see that that's going to work as well. So here we have all of these symmetries. Alright, we've got one last problem. Again, we'll check for x-axis symmetry, y-axis symmetry, and origin symmetry. I would encourage you to try this and then watch the video. Alright, so for x-axis symmetry, we're going to replace y with minus y. We get minus 3y is equal to 2x minus 6. I need that to be a positive 3y, so I'll multiply both sides by -1. Notice our equation is altered or changed, and so no, we don't have x-axis symmetry. When we check with y-axis, or for y-axis symmetry, we'd have 3y equals 2 times minus x, so we're going to replace x with minus x. You get 3y equals negative 2x minus 6. And again, that's not the same as the original equation, so again, we do not have y-axis symmetry. And then finally on this last one, we'll replace both of them, so the y becomes minus y, and x becomes minus x. We'll get negative 3y equals negative 2x minus 6. And again, I need a positive 3y here, so I'll multiply both sides by negative 1. We'll get 3y is equal to 2x plus 6. We got close that time, but we're still not exactly the same. Our equation is not unaltered because of the 6. And so the answer is no. In this case, it doesn't have any of these symmetries. This equation does not. Or the graph of this equation has none of these symmetries. All right. So what we just did is something that you'll run into on occasion in a calculus course when you're talking about symmetries. The thing that we run into more frequently is what we call even and odd functions. It's a more important part of what we do because in college algebra we're concerned about functions. That's what we're working with most of the time. And if you think back to what we looked at previously, when we have symmetry with respect to the x-axis, what we have is not a function. And so really we're going to focus in on these two cases, the last two, origin symmetry and y-axis symmetry, because those are functions. All right, so let's look at this first one here. It says the function f is an even function if f of minus x is equal to f of x for all x in the domain of f. All right, so let me give you an example. If you have f of x equals x squared, so let me just plot those points for that graph real quick. Looks something like that. It's a parabola. All right, so notice we have this point 2, 4, and over here negative 2, 4. And in fact, for any point x, y here, we have minus x, y over here. Now I'm going to write this a different way. We could actually write this point, since we're dealing with a function here, as x and comma f of x. And over here we have minus x. And notice we have the same y value, so we also call that f of x. So whether x is our input or minus x, our output is the same. So that's really what's going on here. So notice what we need to do is plug in minus x. Notice it says if f of minus x equals f of x. So let's plug in minus x here. We get minus x squared, which is equal to x squared. Notice that's equal to f of x, our original function. And so for that reason, this is considered an even function. We replaced x with minus x, and we end up getting the same output, x squared, which is f of x. So I want to make a comment here. The graph of an even function, so this is called an even function because of the fact that it meets this requirement. The graph of an even function is symmetric with respect to the y-axis. All right, let's look down below. It says the function f is an odd function if f of minus x equals minus f of x for all x in the domain of f. So notice we end up doing the same thing. We plug in minus x, but this time we want to see if our output is minus f of x. And so in this case, I'm going to look at the example that we looked at earlier. F of x is equal to x cubed. And remember that graph, it's got a point at 0, 0, 1, 1. If you plug in 2 cubed, that would be 8. So 2, 8 is on the graph. And then if you plug in negative 1 cubed is negative 1. If you plugged in negative 2 cubed is negative 8, and your graph would look like this. And this is what I call the John Travolta. It's the graph of f of x equals x cubed. But again, let's start the same way, because it says plug in minus x for your input. When we do that, we get minus x cubed, which is equal to a negative x cubed. Again, if we multiply minus x times itself 3 times, we're going to get a negative number, and of course 3x's multiplied is x cubed. And so notice this is equal to the opposite of the original function. And so for this reason, this is an odd function. And notice the graph of an odd function is symmetric with respect to the origin. All right, so let's make sure we got this down. To determine if I have an even or odd function, I just replace x with minus x, and I see what my output is. If I get the same function that I started with, like we did with x squared, we plugged in minus x, our output ended up being x squared, or the original function. And so in a case like this, you have an even function, and you have symmetry with respect to the y-axis, or what I call y-axis symmetry. If you plug in minus x as an input, and your output is the opposite of the original function, like we did here, we plugged in minus x, we ended up with minus x cubed, which gave us the opposite output of the original function. This is equal to minus f of x. In this situation, you have an odd function which has symmetry with respect to the origin. So these are the two tests that we tend to do when we talk about symmetry. If we have an odd or even function, that tells us about the symmetry. And these are both functions, so that's why these are the ones we care about. All right, so let's go to the last page of the notes here. So notice what it says. Determine whether each of the following functions is even, odd, or neither. Then determine if the graph is symmetric with respect to the y-axis, the origin, or neither. So on number 1, we'll replace x with minus x. So notice what happens here. If you cube negative x, that's negative x cubed times 2. You're going to get negative 2x cubed. And minus a minus x becomes plus x. Now you really could stop here if you want, because notice our first term has the opposite sign, and our second term has the opposite sign. And so this is equal to the opposite of the original function. Now you could go one more step and you could write it like this. Usually I just stop here, but you can see that when we replace x with minus x, our output is the opposite of f of x, or the original function. Each of these terms change signs. So this is a case where we have origin symmetry, and so that means, oh, and I'm sorry, this also means that we're an odd function. So this proves that we have an odd function, which tells us we have origin symmetry. I got these two turned around backwards. All right, let's look at number 2. So let's replace. So you'll notice the test is the same for each one of these. We plug in minus x. So all of our x's get replaced with a minus x. So we have f of x equals minus x to the 4th plus 3 times minus x minus 2. So we get x to the 4th. Now this is squared. I forgot my 2. So notice a minus x times minus x is x squared. This is going to be plus 3x squared minus 2. And so notice our output is unchanged by plugging in minus x. We get the same thing as with the original function, or you could say we're equal to f of x, the original function. And so this is a case where we have an even function. And so we would say we have y-axis symmetry. Or you could write symmetry with respect to the y-axis. All right, why don't you try number 3 if you haven't already. All right, let's see how you did. So when I plug in minus x for x, if you multiply 5 of these minus x's, you're going to get a negative number, and 5x's multiplied is x to the 5th. So we get minus x to the 5th minus 3. Now notice that's not equal to the original function, and it's not the opposite of the original function. The opposite would have been minus x to the 5th plus 3. And so in this case, we have neither an odd nor an even function, which means we don't have any of these symmetries. So we could say, we don't have y-axis or origin symmetry. We'll say neither for that as well. All right, so that's how you determine if a function's even or odd. If it's even, you have y-axis symmetry. If it's odd, you have origin symmetry. All right, let's look at this last problem. This is similar to one problem you'll see, or at least one in the homework. Find the point that is symmetric to the given point with respect to the x-axis, the y-axis, and the origin. So let's put the 3 cases, x-axis, y-axis, and the origin. And let's go ahead and graph this point. So we're at -2, 3. So this is the point, -2, 3. So find the point that is symmetric to the given point with respect to the x-axis, y-axis, and the origin. So with respect to the x-axis, this is the x-axis, we would be 2 down. Oh no, I guess it's 3 down. So that would put us here at -2, -3. So that's the point that's symmetric to this point with respect to the x-axis. So again, our focus is on this point here. This is the one we started with. I want to find the point that's symmetric to this point with respect to the y-axis. Well, if you look at the mirror image through the y-axis, that's going to put you over here at this point, 2, 3. And so that would be the point that goes here. Finally, we need to find the point that's symmetric to this point with respect to the origin. Well, again, you could draw a line that goes through the origin to the opposite side. Notice that's going to put you at 2, negative 3. And so that's the point that you find that's symmetric to this point with respect to the origin, which is basically this single point. All right, so that's it for this video. If you have any questions, let me know.